Hello, we are HARP, a high-altitude research project, a student-led project with the goal of developing a payload capable of reaching 100,000 feet in order to collect atmospheric data such as 2D and 3D winds, which will further help in development of a global set of data around high-altitude turbulence. In addition, this project is working in collaboration with NASA's HASP program, the High Altitude Student Platform Program, an international competition allowing student payloads to be placed on a weather balloon and safely transported to high altitude regions of the atmosphere in order to collect scientific data that the students provide. Overall, because these wind measurements are occurring at low pressure regions, these findings can help teams learn how to measure low pressure atmospheres, such as Mars, to help model atmospheric turbulence for future interplanetary UAV missions.
Throughout the duration of our senior design project, we actually faced many challenges, and one of those is being the sensor selection. Due to the low pressure conditions at operating altitude, we had some challenging selecting the correct sensors in order to measure the wind turbulence. Through numerous case studies, we decided to set on a 3D ultrasonic anemometer for our main sensor choice. This was later reviewed by NASA HASP reviewers, and they said that this was a good choice of sensor. We also recently learned that the NASA Balloon Program Office has started using ultrasonic anemometers to measure wind at high altitudes. This shows that we overcame this challenging part of the project. In addition to that, there was also issues with the payload design. The design must not block or create a lot of disturbance of the airflow around the sensors. So the first concept was to have arms with thermal wind sensors on the end configured for 6 degrees of freedom. However, this was outside the max dimensions for NASA HASP, so we had to redesign to the current halo. HASP approved the halo design, showing that we provided sufficient scientific data and reasoning on why our design must be like this. Finally, I think which would be the most major challenges that we faced is our team was comprised of 5 aerospace engineers and 1 applied physicist. We all have various skill sets, but we are all very specialized in them, so we had to learn new skill sets to ensure the project was successful. Some members had to improve with SolidWorks, learn concepts for power management and radio frequency and telemetry link technologies, and new coding language such as Python and Arduino. This provided us amazing lessons, not just academically, but also life lessons that we will carry into our future careers as we enter the future workforce.
As aerodynamics lead, what do you think the biggest challenge you faced was when developing a flight plan for the payload?
How unpredictable the wind can be from day to day. So some days it would be blowing harder or not as much, or it was blowing northeast or southeast. So our payload would sometimes land in Mexico or New Mexico or high north Arizona. And that was just from day to day. And our flight planner wasn't able to predict further than a week out, so we just had to kind of run different tests on different days, not our actual flight date. So it made it difficult to kind of get a concrete idea of where we wanted to launch from, and also avoiding restricted airspaces, landing on land that we weren't going to be able to retrieve it easily, and also trying to get it near an interstate or a highway or somewhere where we could drive up to it and hopefully not have to travel very far. Was probably the most challenging thing that we faced when developing a flight plan.
During the first drop test, there was a complication. What happened?
Unfortunately, for our first drop test with our actual payload, the parachute did not deploy properly and it led to an increased velocity at landing. This was caused by a shortened cord between the actual parachute canopy and the payload. We shortened it because we with such a low dropping height, we wanted the parachute to have the most amount of time and space to create drag. Unfortunately, we tied it too close to the payload, and it caused the cords to pull down and not deploy fully. So the drag wasn't sufficient to slow the payload down. We then retrieved the payload, redid it with a longer cord, and it was a successful drop test.
Based on the mission and mechanical design, we first choose a 3D analog meters for our wing measurements and also as a backup altitude and depression meters. It's relatively accurate and result performance at our working condition, which with its minimum weight and well design, make this the best option for our main sensors. For the backup sensor, we want a higher accuracy. Those within the budget limit, we choose thermal resistant-based wing sensors. With a proper signal processing and machine learning skill, you can achieve a magnitude higher accuracy compared to our main sensors. Surrounding our sensor selection and the mission, we design an electrical system that will have a microcontroller unit collecting data from sensor, and then transforming it to a Raspberry Pi, which will act as a database. Then you will also transmit the data to the communication system based on RP900, which that will allows us to receive data at ground stations. The internal wires are mainly based on CAN line and the USB serial connections. We have two self-power systems, which one will power the main sensor units, including Raspberry Pi, and the second one will power the communication and pixel hall system. This allows us, even with the main power shutdown, we can still are able to control the balloon release mechanism and have a GPS tracking to recovering the balloon. In summary, our electrical system managed to successfully work in all the working conditions. It also provides redundancy and also the communication between the payload and the ground stations. In conclusion, our project is being accepted into NASA has international competition. Using the FEA analysis and the mechanical design skill, our mechanical design of the box is successfully be proven reliable at the given forces. Next step is to do a local test for a local airfield to ensure all the electrical system and mechanical design work in the mission conditions. The future work of this project is to have the proper data analysis. The system can be collect data at the mission conditions and have enough computing power to calculate the finalized data of the wind turbulence. Those we can call the success of our projects.